My name is Gary Fredericks. Welcome to my talk. I write Clojure code at Groupon, and this is an introductory talk to macros. So I want to talk about macros because for me, when I first understood how macros work, it felt like that corresponded to finally understanding what the actual semantics of Clojure are and how Clojure works. They're also the major selling point of Lisp and homoiconicity, but they can be quite intimidating for beginners. You have to juggle in your mind the difference between compile time and runtime, and the primary tool for writing macros, called syntax quote, looks very syntactically confusing. And also there's lots of talk about what is appropriate use of macros. People say don't write macros at all and this sort of thing. So I wanted to go into all of these issues and hopefully leave you in a better place to understand what you're looking at and maybe write some of your own. So we're going to go over the primary background concept, which is that code is data. Then we'll talk about how macros work in Clojure, and then the appropriate use question. With some ideas for that, and we'll finish up by looking in detail at syntax quote. Okay, so getting right to it, I think I'll have time for interruptory questions. So if you see something that doesn't make sense, you can try raising your hand or yell at me if I don't see you very well. Code is data, something that we've probably all heard and are somewhat familiar with, but it's crucial to understanding macros, so I want to make sure we get it solid. Data we're familiar with. This is a map with keywords and some things. It has just one meaning, but our code is also data, and so it kind of has two meanings. The meaning at runtime that we're familiar with is that this is defines a function. It has a doc string, and it takes an argument, and then it does some things and returns maybe a Boolean or something like that. But at compile time, this has a different meaning, which is that it's a list, which is what's indicated by the parentheses. The first two things in the list are symbols, and even though defn is something that's in Clojure core and secure password is something we made up, they're both just regular symbols. Third thing is a string, and then we have a vector with another symbol, and then another nested list with some more symbols and things, and the dot contains on line 6 and 7, even though they mean something really special at runtime, are just another symbol at compile time. So I'm going to start using the word form to refer to this code data. So when you have code that you're manipulating as data, I'm going to call that a form. So how do we get these forms? Because normally, like on line 1, if we enter some code at the REPL, it's going to be evaluated immediately and we'll get a result. We don't have the code to mess with at any point. And so this is what quote does. So on line 3, if we use the quote special form and have a form inside of it, it's going to return the code itself. So that's a list with a symbol and then 3 numbers. The single quote apostrophe does exactly the same thing. And that equivalence is something we'll have to keep in mind because we want to use the single quote because it's easier, it's one character, we don't have extra parentheses, but it's not sufficient for everything. And of course on line 7, if we have some nested code inside of a quoted expression, it still doesn't get evaluated. You can also get forms by using the reader. So if you call read string on a string with some Clojure code inside of it, then you're going to get the data structure returned. If you read a string with foo, you'll get a symbol. And more interesting, on line 10, if you read a string that has a single quote in foo, you're going to get back a list with the symbol quote and the symbol foo in it. So the correspondence between the single quote form and the long form quote is at the reader level. Because code is data, we can build and manipulate code like data. So we can use our familiar functions. We can take a form and reverse it to get something that's not actually valid code, but we can still do it. You can take the first 2 items in a list, that sort of thing. If you want to take a value at runtime and stick it into a form, what we're doing on line 7 is not going to work, and it shouldn't because there's no way for Clojure to know that the word num is different from the other things in the list. What we can do is, instead of quoting a whole list, we can use the list function to build a list and then quote the things that go into it. So here on line 2, we're calling list, and we have each of the symbols going into the list quoted except for num, which we want inserted from the local scope. So that's how we get the number 5 in there. Once we have forms, we can run them by using the eval function. So if you pass a quoted piece of code to eval, it's going to get run like you're used to. If you take some code that's not valid and then reverse it so that it is, you can eval that. On line 6, we have a form that contains an X, which doesn't normally mean anything. And so if you pass it to eval, the compiler is going to complain that it doesn't mean anything. But we can, for example, use let to give it some meaning. So if we want to build a let expression that's just a list, so we start by making a list with the symbol let at the front, and then a quoted vector with x and some constant. And then we insert our not compiling form as the last thing in the list, and we'll see on line 2, the result is something that looks like valid code. And indeed, if we eval it, it will run and give us a result. So you can do more complicated things like quote things several times and eval things several times. And if this is uncomfortable, then I encourage you to go to the REPL and just play around with it, because this is the building blocks for what macros are doing. And it would be tricky to understand macros without having a good grasp of this sort of thing. So with that out of the way, what is a macro exactly? Macro is a special function. When you see a macro call, it's a parenthesized thing with the macro name at the front and then some arguments. And the compiler is going to pass those arguments as forms into the macro at compile time. It's expecting the macro to return a form, and then the macro call is going to be completely replaced at compile time with whatever the macro returned. So this only gets called once for any given macro call that you see in your code. And effectively, the macro does not exist at runtime. And one of the implications of this is that macros are basically never necessary to make your code do something. You can always replace this macro call with whatever the macro expands to. The macros are really only necessary to make your code look like something, so it's a syntactic thing. We have a couple examples of macro calls on the left side of the table from closure core macros and the expanded code on the right side. Any questions so far? All right. Another expansion example, Project Euler problem number 4 asks to find the largest palindrome made from the product of two 3-digit numbers. So you can do most of the work here with a 5-line for expression that loops over all the 3-digit x's and the 3-digit y's that are less than x, and then multiplies them together to get an intermediate value and filters on that being a palindrome, and then collects all the results together. So this is pretty dense code. But 4 is just a closure macro, so that means it expands to something. And in this case, it expands to that, which is, granted, most of the tedium here is just because of some low-level optimizations, but this isn't even fully expanded because there are other macro calls inside of this that haven't themselves been expanded. So the point is we can use macros to remove a lot of tedium from syntactic tedium from the code we write and effectively add features to the language. So let's go into the mechanics of writing closure macros. So what we're going to start with is to try writing a function that takes forms and returns a form. So a classic macro example is unless. In this case, it's just equivalent to closures if not, I believe. But we're going to do it anyways. Unless is like if, but it has the false case and the true case reversed. So we take 3 arguments, the condition and the false case and the true case, and what we want to do is return an if expression. So we create a list with if at the front, and then the condition, and then the true case and the false case in the opposite order that they were passed in. We can try using this, but we can't use it the normal way. Because if we use it like this, then this equals function is being called and evaluates to false, and then the print lines run and they return nil, and so we pass in false and 2 nils, and both the things print and we get returned if false nil nil, which is not what we wanted. But we know how to pass in code, we need to quote it. So if we do that, we will get returned the expression that we want in this case, which is the if like the unless, but with the clauses reversed. But we haven't had any side effects because we haven't run this, so we can run it by passing it to eval. And then we get the behavior we want. So it works, but it's terrible and you wouldn't want to use this. So fortunately, this is exactly what macros do. So we can try rewriting it as a macro. Here's the function version on the left that we just wrote and the macro version on the right. And if you look closely, you'll see that they are completely identical, except that we've swapped the word defn for def-macro. So macros really can be written as just functions that take forms and return forms. And once we've written it as a macro, we can start using it in the more comfortable way, where we just put the code there, the code unquoted, and we don't have to eval anything, and it works fine. But now we've lost the introspection of seeing what the macro returns. We don't know what the expanded code looks like. And so fortunately, for the sake of debugging, there's a built-in closure core function called macroExpand1. You can pass it the form of a macro call, and it will return to you the expanded code. So this is great for developing macros. Instead of running them and seeing something that's kind of indirectly related to the macro you wrote, you can actually see the results of your pure function macro. Moving on to a more extended example, we want a macro called spy, which is going to be a debugging tool. This doesn't exist in Closure Core, but I've seen it defined in a few places. The idea is that we want to be able to wrap an expression with the spy macro and have it print the code and the value of the expression and then return the value. So that way we can wrap anything anywhere in our code with spy and the code will still work as it normally does, but with the helpful debugging message. So for sanity check, let's make sure that we can't do this as a function. We can try writing a function called spy that takes an expression and prints that the expression is the value, and we can tell this probably shouldn't work because on line 3 we have the expr written the same way both times, so we shouldn't expect it to do two different things. And indeed, when we run this, we get on line 8, 42 is 42, which is certainly not what we wanted. We can try quoting the first one, but if we do this, all we're really doing on line 3 is quoting the symbol expr and passing that in to print line, and so we get printed expr is 42, also not what we wanted. It's not very surprising that we can't do this with a function because it's a macros talk, but it's worth noting that we can get the functionality by adding a bit of repetition. So if we take 2 arguments instead of 1, and we have the user pass in both the code and the value, then we can print the code and the value together and get the same behavior at the expense of some syntactic repetition. So let's try writing this as a macro. When you want to write a macro, usually the most straightforward approach is to think about how you want it to be called, what you want the macro call to look like. So that's what we have on line 1. And then what you want that macro call to expand to. How would you write the same code, but without the macro? So in this case, we want to use a let because we want to store the value once and then use it twice, once in the print line and once when we return. So we have the let, and we put the expression there. We name it val, and we call print line with the expression again, but this time quoted, and then we return the value. So if we want to have a macro that creates a let expression, we can use list with let. And then on line 4, we have a vector with val quoted and then expression not quoted, so that the expression gets inserted into our form from the macro argument. And then on line 5, we have our print line call, with the expression quoted there, and then we return the value. And we can look at the expansion on the right-hand side. And the interesting point is line 6. What we got is that the symbol expression ended up in our form, and that doesn't mean anything in this context. And so if we run this, we're going to get a compile error saying, I don't know what expr means. That shouldn't be surprising because line 5 on the left, we quoted expr in the same way that we quoted print line and val, so we should expect that they'd all 3 make their way into the form in the same way. So that's clearly not how this was meant to be written. Let's try doing something different. We can remove the quote on the left side. So line 5, we have no quote around EXPR. If we look at the expansion on the right, the result is that the code has now been inserted both on line 5 and line 6 in the same way. And so now the effect is that this code is going to be run twice, and the print message is going to just say 42 is 42. So that's also not what we want. So we've tried quoting it once and 0 times. We may as well try quoting it twice. What we're going to get now is that the expansion on the right has the list quote EXPR, which is now just quoting the symbol EXPR. Now this will compile, but the message is going to say EXPR is 42, which is again not what we wanted. So what's going on here? Why is this confusing? The key issue is this equivalence between the single quote and the longhand quote form. So if we look at the expanded code we want on the left with the single quote, and then the same version on the right with the long form quote, that might give us some more ideas about what else to try, because this longhand form is just a list with the symbol quote and then the thing we want quoted. So we could try actually building that list. If we do that on line 6 on the left, we create a list with the symbol quote and then the expression. And the expansion then on the right expands into a quote with our code inside of it, and so that's going to end up passing the code into print line. And this works correctly. So I guess the lesson is that these things can be somewhat subtle. To preview syntax quote, if you think the definition on the left is a little difficult to read and clunky, that is what syntax quote is for, and this is the syntax quoted version on the right. Is a lot nicer once you get used to it, and it also takes care of a couple issues with macros that we'll go over. So wrapping up this section, what can you not do with macros? A lot of things, actually. You can't mess with the reader at all. You can't change the behavior of code you don't control. Really, the only thing you can do is mess with the code inside your macro call. You can do arbitrary things to that, but that's about it. In particular, if your macro is being called inside another macro call, then that outer macro is going to have first dibs on doing whatever it wants to your macro call, and maybe your macro will end up not even getting called. And you can't change that. That's really the way it should be. So that's it for that section. Any questions?
Yeah. So if the macro runs like a function during compile time, what does it have access to in the environment?
Basically everything. It's, with a few caveats, it's just basically a regular closure function. In fact, you can have side effects. You can do all sorts of naughty things if you want.
Does it have the functions that are defined in the same namespace or in the same file?
Yes. Yeah, you can. I mean, yeah. So sometimes you'll have, say, helper functions that you'll call at macro expand time. And so then, the fact that those were defined before you define your macro allows you to call them. And maybe they're just regular functions, but they also take forms and return forms, and you're using them to help build the final return value from your macro. So you can do things like that. Anything else?
Are you going to show the syntax quoted version again?
At the end, yes. Okay. So I'm going to talk now about the question of why you might not want to write a macro or when you should use macros. We'll go over common macro usages and how to avoid macros, this sort of thing. So Stu Holloway famously said in his classic book that the first rule of Macro Club is don't write macros. So why would he say such a thing? Macros are not functions. There are lots of nice functional patterns that functional programming is built around, and macros can't participate in this. We said before, the macro effectively does not exist at runtime. It's something that happens once at compile time, so the idea of passing the macro to a higher order function doesn't really make sense. So you've probably seen this error before, that you can't take the value of a macro. You can wrap the macro call in a function. And if you get tired of that, you can write a macro to do this for you. And so you can use now macro reduce and you pass it or and even special forms like do, even though that doesn't make much sense. And it just works. And this happens in other places. So if you use close your test like I do, there's an is macro there. And I'm always saying is equal these two things. And so that gets a little repetitive. Maybe I just want an is equal thing. And the only right way to do that is to write another macro. So why is this bad? Macros can make your code hard to understand. And we'll talk about it. They're essentially, each macro is another language feature. So as the person reading the code, you have to have a special case in your head for each macro that's being used. Basically, we want to try to avoid macros unless we really need them. They tend to be difficult to use, difficult to compose without writing more macros, and it can make your code difficult to read. However, there are lots of macros, and we use them all the time. A lot of macros are for wrapping execution. These are often named with the prefix with or some sort of adverb. You can delay execution with a macro, so delay future and lazy seek will take the code you pass in and wrap it up in a function and then keep that for later and maybe call it some other time. Lots of macros are used for defing things because you effectively cannot def something from a function, so you can use a macro for that, and these are often named with def as well. You can use macros for capturing code that you wouldn't otherwise have access to if you were just writing a function. So assert does this. So it can stick the code into the exception message. The spy macro we just wrote does this. Closure tests is macro will take the code and print it when your test fails. Macros are great for DSLs. I'm sure you're familiar with Korma or Composure or Midge that all use macros. Really interesting use of macros is compile time optimizations. So Hiccup, which generates HTML from data structures, the HTML macro, if you call it with data structure literals, it will notice that at compile time and do as much as it can to generate as much of the HTML as is possible at compile time, so it doesn't have to do that again. And the same with the string interpolation function in the core incubator library. You give it this string that has some special stuff in it, and it's going to parse it at compile time, so it doesn't have to do that every time you call. The comment macro just always returns nil. The assert macro is really interesting. It throws an exception if the thing you pass in is false. But there's an assert var with the earmuffs that you can turn off. And if you turn it off, then all of the assert statements just emit nil. And so effectively, you can use asserts all you want without worrying that it's going to slow you down, because if you have performance problems, you can just turn them off and they go away. And of course, if you're implementing entirely different paradigms, you can be forgiven a few macros. So ideas for not writing macros. I think mostly this just boils down to learning functional patterns. There's lots of interesting ways to do things with higher order functions. There are other functional languages that don't have macros and they somehow manage. One interesting idea is instead of using wrapper macros, you can use function decorators like Ring does with its middleware and close your test with fixtures. You can learn more about the macros that already exist, so you're not reinventing the wheel or reinventing something that's just basically this other thing but slightly different. For example, there's some interesting threading macros that were introduced in Closure 1.5. And also, just don't get obsessed with trying to eliminate all repetition everywhere from your code. Learn to tolerate a little bit of it for the sake of simplicity. But if you must write a macro, there's a number of ways to do it in a sane way that is what people expect. So one idea is helper functions. So if macros are difficult to reason about, you can often write a macro that does just the tiny bit that you need a macro for. So a lot of macros can be 1 or 2 lines, and then have a function that does most of the functionality but without the syntax sugar. and so your macro expands into a call to that helper function. Also good naming conventions. I mentioned the adverbs and the defing naming convention. Although a lot of times if you think you need a def something macro, you might be able to get away with either a macro or a function that doesn't def anything and then just use def by itself. If you're going to def something, then please just def one thing and have the user name it. And then another temptation is introducing magical locals. The standard convention is to only introduce locals that are named by the user. So if the user's going to call a macro and have something be defined in their local scope, then they should name it as well. So it's explicit where the thing came from. And also, there's rarely any reason for a macro to have side effects. I was looking at the slide earlier today and realized that most of these things are violated by closure somewhere. But I think that falls under the rich can do whatever he wants rule. So I think we're all done with that section. Any questions? Okay, syntax quote. Syntax quote is the primary tool for writing safe and readable macros, but it's a little intimidating at first. So it's basically an enhanced version of the single quote. You use it with the backtick character, and you use it syntactically the same way you use single quotes. So you just stick it in front of a form, and that form is going to be quoted with some extra things thrown in. There's basically three pieces of functionality that syntax quote gives you. There's unquoting, there's symbol qualification, and auto Gensym. I'm going to go through all three of these, and as I'm discussing each one, I'm going to be totally ignoring the existence of the other two because the examples would be a lot more complicated if I had to constantly explain what was going on. So most of the code examples are going to pretend that there's just one thing happening, and then we'll tie it all together at the end. So unquoting, we already saw the problem we need to solve here. Our spy macro is very difficult to read. We have all these calls to list and all these things we had to remember to quote. And it kind of suggests some sort of templating solution. So that's exactly what we're getting from syntax quote with unquote. So on the left we have our old version. On the right we have the syntax quoted version. All we're doing is the whole body of the macro is just this syntax quote expression, and it's basically the code we want to return with the exception of this tilde syntax we're using to insert the expression from the macro argument into our form. And interestingly, on line 4, the single quote versus long form quote thing that we were messing with earlier isn't actually an issue here. Because of the way syntax quote, unquote, and the single quote all interact with each other, this ends up working. It's still a good thing to keep in mind and to do sanity checks to make sure it's doing what you think it is. In this case, as in the comment there, you could have written it either way and it would still do what we want. Unquote-Splicing is the other half of this feature. So in order to motivate this, we're going to look at another macro that I took from the Flatland useful library. It's called returning. It's basically the opposite of do, where you put the return value as the first thing instead of the last thing. So the idea is I'm going to specify what I want to return from the expression and then have some unrelated side effects that I want to run afterwards. So what should the expansion be here? We're going to want to use a let. Because we want the thing to run before the side effects. So we can't just use do and switch the thing around. But we'll have a let where we run the code and stick it in a local val and then run the side effects and then return the val. And the interesting point here is that we don't want to restrict the user to exactly 2 side effects. And we don't want to enumerate all the possibilities. We want to use var args. So here's our definition on the left side. Our macro has the expression argument and then the var args for the side effects. And the interesting point here is that var args will return as a list, and so side effects has a value of a list of forms. So if we unquote side effects on line 4, then the expansion on the right-hand side has these forms in a list with an extra pair of parentheses. That we didn't want. And this will cause either a runtime error or just some really bizarre behavior. So we can get around this by constructing the form using concat instead of using syntax quote. So this works, but it's terribly ugly and confusing, and we want to use syntax quote. So fortunately, unquote splicing does this for us. if we, this is on the left side identical to 2 slides ago, except we're now using tilde @ sign instead of tilde on line 4. And so the semantics of unquote-splicing are that we expect the thing that you're evaluating there to be a sequence of some kind, and then it's going to be inserted into the higher level container as actual elements instead of a single list. And so you can see the expansion on the right. This does what we want and it works correctly. If this still confuses you, a lot of people have trouble with this, I think. Syntax quote is not tied to defining macros. You can play with it at the REPL just like you can single quote. And so that's a good way to do sanity checks and make sure you understand what's going on. So the second feature of syntax quote is symbol qualification. So the primary issue that this addresses is when you have a macro defined in one namespace and it's being used in another namespace. Because what we're used to in Clojure is that a symbol, if it's not fully qualified, then its meaning is relative to the namespace it's used in. In this particular example, the only interesting symbol we're using in our returning macro is let, which happens to normally refer to clojure.core/let. And that's certainly what we mean when we define the macro, but perhaps it's being used in this other namespace on the right where this guy wants this funky version of let from some other library. And so in his namespace, let refers to something else. And that's not something that macro authors should have to worry about, and certainly not something macro users should have to worry about. So the naive way to get around this is to just have the macro author on the left side write clojure.core/let, be totally unambiguous. But that would be tedious. We don't want to do that. So fortunately, syntax quote does this for us. When you syntax quote a symbol, it will automatically expand it based on what it means in the context where you're using it. So if you syntax quote first, you get Clojure core first, assuming that's what first means in your namespace. Foo will expand to user foo unless it means something else. If you expand if, because it's a special form, it doesn't have to be expanded. If you syntax quote a whole list with symbols inside of it, then those will all be expanded as well. So the effect is that if you're using syntax quote, this problem tends to be solved for you and you don't have to think about it. So when we write our macro with syntax quote on the left, the expansion on the right already has clojure.core/let. And this tends to just work. The third feature is auto Gensym. So the problem here is kind of similar to the last problem, but this is about locals instead of vars. So if your macro creates a local and the user's code runs with that local in scope, then you can have some interesting shadowing issues and things not doing what you want. So for example, this doMath function wants to use the returning macro. It takes a single argument called val, which happens to be the exact same local name we used in our macro definition. So what we want this to do is return 7 times the argument and then print that it multiplied 7 with the argument. But when we pass in 2, it tells us that it multiplied 7 with 14. Why does it do that? Well, if we look at the expansion, what we basically wrote was a function with an argument and then let the same name. So by the time we get to line 11, val refers to the new val from line 10 and not to the original argument. You can fix this naively by just having the macro author use a sufficiently obscure local name, but that's again not very ideal. So fortunately, syntax quote handles this as well. If you put a hash sign at the end of a symbol, it will automatically turn it into a Gensym for you. And helpfully, on line 3, if you use the same name for a Gensym more than once, it will expand it to the same thing. And on line 7, if you have 2 separate syntax quotes, then it's going to expand differently, which is good because that allows macros to work together without conflict. Using this here, looking at the expansion, we've now switched to using val with the hash sign in our syntax quote on lines 3 and 5. And then in the expansion, we see we've got the original val that the function writer used on line 9 and on line 11. So line 11 val still refers to the argument, while line 12, the Gensym val, refers to the new val that we had created in line 10. So this is good. This lets us avoid that problem. A lot of people, when they're writing macros, 5 minutes. We'll get confused about when to use this feature. It's basically whenever you create a local in your macro. You can also think of it as whenever you don't want things to be expanded into a fully qualified symbol. And fortunately, this is difficult to forget because the compiler is going to end up telling you that you can't let a fully qualified symbol because this thing will get expanded when you didn't mean it to. And you just have to watch out for that particular error. So this is the different features for syntax quote we just went over. The tilde by itself does a regular unquote. The tilde with the @ sign does Unquote-Splicing. A symbol by itself is going to get fully qualified based on the context, and a symbol with the hash sign will get turned into a Gensym. So if we bring this all together for our spy macro, we're now using syntax quote. We use unquote for the expression arguments in both places, and we use the hash sign for the local val that we create. And the two vars we're referring to, let and print line, both get expanded into the full closure core versions. So the expansion on the right has all three of those things, but it's now a little less readable because of the expansions in the Gensym. So that is one downside to this. I think that's a problem that tools can solve, development tools, and maybe already do, and I'm just not familiar with them. But fortunately, it's safer and more correct. I've got a few minutes left. A couple fun slides. If you start nesting syntax quotes, you get interesting behavior. In particular, the size of the form that gets returned is exponential in the number of quotes, so this is a great way to crash a REPL or a reader or anything that evals code. So if you do about 8 or 9, you're going to start getting stack overflows or out-of-memory errors or that sort of thing. Another interesting thing is if you're familiar with the threading macros, they have an interesting recursive definition, which the top form here is, this isn't something you would ever need to write, but it so happens that if you expand it twice, you get something that's basically equivalent but reversed. If you expand it 4 times, you get the same thing. So if you feed this into your closure code, then you're going to get an infinite loop in the macro expander. So it could be fun to look at the definition for this threading macro to figure out why it does that. I think I'm going to skip through the last couple of these. So wrapping up, things I totally left out, there are 2 magical arguments to every macro that are not normally needed, but if you want to really understand how macros work, then you should know about those. There's also a good contrib library that has a couple extra interesting features. We've been talking about macros. Macros, by taking advantage of Lisp and homoiconicity, let you reduce all the some of the syntactic repetition in your code. But they can be difficult to write because you have to understand the difference between compile time and runtime, and you're basically adding features to the language, and a language with too many features is not typically a good thing. So you have to keep the usage in check. And also, syntax quote is a great tool when you do have to write macros. So that's all I have.